Hey, grade 12s, cool. So if organic reactions is getting a bit confusing at the moment, we're about to break down question 4 here of the June 2025 chemistry paper, where we're going to see the usual structure of a question like this, as well as revise some of the sections and get some useful tips to help us orient ourselves as we work through this question. Okay, let's jump right in. So question 4 says, the flow diagram below shows how an alkene, can be used to prepare other organic compounds. The letters J to N represent various organic reactions. So this main guy here, it is an alkene. It looks something like this. So we have our meth, eth, prop, bute. So we have butene, and because this is on the first C over here, we can call it but1-ene, or we can just call it butene. A reminder that alkenes end in ene over here. So now that we can visualize what alkene we're dealing with, let's move to 4.1, where they are asking the first question having to do with the fact that this is an alkene. So 4.1 says, is an alkene a saturated or unsaturated hydrocarbon? Explain the answer. So 1 mark for the correct answer, and then 2 marks for the definition of whichever answer we pick, provided it is correct. So a nice way that I like to think about this, we have saturated versus unsaturated, and I sat down to sing is a little memory device that I use in order to remember that saturated are just single bonds compared to unsaturated, which also have double or triple bonds in the mix, which means our answer for an alkene has double bonds, which means we're dealing with an unsaturated molecule. So we just earned 1 mark for unsaturated, and then we just need to go ahead and write the definition for unsaturated, which is exactly what we were talking about now, where there are 1 or more multiple bonds, i.e. double or triple bonds, between 2 carbon atoms in the hydrocarbon chain. Great. So 1 mark for unsaturated, and then 2 marks for this over here, with 1 or more multiple bonds between 2 carbon atoms in the hydrocarbon chain. Okay, and they're always trying to squeeze some sort of definition into the first question of each of these sections, even if they don't phrase it as write the definition of unsaturated or saturated, for example. So this just earned us 3 marks. And then 4.2 over here says write down the type of reaction represented by. Okay, so we have a bunch of different letters going all over the place from this alkene, and we just need to see what has been added or removed or substituted in order to get the products on the other side of the arrows. Okay, a reminder that for this section, we don't have to be specific with which type of reaction it is. By that, I mean we can use the general terms addition, elimination, and substitution. We don't have to say hydration, dehydration, dehydrohalogenation. We can if we remember it, but we can always work with one of these big umbrella terms. It makes it a little bit easier for me because a nice way that I like to remember it is that addition goes from 2 things to 1 thing, and elimination goes from 1 thing to 2 things, and then substitution is a 1 to 1 or a 2 to 2. By this, I mean in order for an addition to take place, we will need something like a double bond over here, because this double bond needs to break, and we need this plus something else, say a haloalkane or just a halogen or something like that, or a hydrogen, to break this bond and then form here, which means we would need this plus something in order to make 1 new thing. An addition means we have to look for any double or triple bonds, usually just looking at double bonds. Okay, elimination is just backwards of that, meaning we would have a single bond, and that single bond would exist, and we would remove something, and the only way this will still make sense is by adding a double bond back to it, which means we'd have 1 thing, we would remove something, and that something would live on this side, along with the thing that now has a double bond, meaning addition has a double bond over here where the 2 lives, and the elimination has a double bond over here where the 2 lives. And that's a nice way to remember that 2 is a double bond for addition and elimination. And then substitution, we can just deal with that by itself, considering that is just a 1 to 1. It means we're just swapping something for something else, meaning that we are going to remove, say now this H here, and just put a Cl in its place. But we haven't changed the main chain by any stretch. We haven't removed any double bonds or created any double bonds in doing that, which meant it goes from 1 to 1 or 2 to 2, and there aren't any bonds breaking on the main chain like addition and elimination. Okay, so with that, this makes it a bit easier for me to just keep this in mind as we approach these questions, because then I can see a lot easier what sort of patterns we're working with in order to deal with that. And then if we remember the specific names, then we can add them by all means. But this helps us and makes it a lot easier to study so that we can save time in our studies and focus on other sections. reactions as well. So with that, 4.2, write down the type of reaction represented by. 4.2.1, we have J over here. So a reminder that this is the but1ene that we're dealing with, and then something happens. Sometimes they draw the thing on the line, sometimes they don't. But in this case, this plus something maybe goes to butane, which means that we went from but1ene to butane. And in order for that to happen and this double bond to break, for a single bond to live there, we would have to add something, because a double bond going to a single bond, remember that fits the brief of over here, 2 to 1, addition 2 to 1. So we have to add something. And in order for this double bond to break and for this to still make sense, by that I mean there will now be a new H that can live here and a new H that can live here, because this H and this H, these two guys, weren't required for the but1ene, but they are required now for the butane, considering this double bond went away and two new availabilities opened up on these two carbons, so that they both had 4 lines around each carbon, which means that we had to add an H2, because an H2 is missing in order to fill this gap over here and these empty spots. Okay, which means that that understanding helps us a lot, meaning that it is hydrogenation, should we want to write that down. But in a test, if we don't want to work all of that out, we can just see that there was a double bond and now there is no double bond, and that means it is just addition. So we can either write addition or hydrogenation, both will give us the mark. But if we see that it went from a double bond to a single bond, it means that it is addition, and we'll get our 1 mark for just writing addition over here. Okay, so we just earned 1 mark over there. And then 4.2.2, so the type of reaction represented by K over here. So K is from butane to compound Q. And there's not very much information, considering here we had information before, nothing on the line, and then something there. So we had 2 slots, and then there was a missing piece over here. Right now, we have something before, nothing on the line, and nothing afterwards. So that means there isn't enough information to figure out what happened at this stage or what happens at this stage. If they gave us something on this line, we could happily figure out what happens at compound Q, like butane plus something equals compound Q. But in this case, there isn't enough on this line, so we need to try and find another way to get to compound Q so we can understand what compound Q actually is. Because if let's go from here first, our alcohol to compound Q also isn't enough information to figure out what Q is. But from the middle here, we have this alkene over here, this but1ene plus HBr, and then we form the same thing that this butane plus something will form. Okay, that means we have to use this information plus this information to figure out what compound Q is, and then we can figure out what reaction had to take place to create compound Q from butane. Okay, so that means if we're looking at our alkene here and we're adding an HBr, it is quite similar to this previous reaction, considering we had a double bond, and in this previous case we added an H2. That was our hydrogen, our hydrogenation. But here we're adding an H and a Br, which will serve the same purpose as removing a double bond over there and creating this opening and this opening here for an H to join and a Br to join. Okay, which means we're ending with a product like this for our compound Q. Our compound Q then is 2-bromo-butane, which means we can remove this because there's no longer a double bond over there, and we can just add our ane over here, which means compound Q is this guy, 2-bromo-butane, because we have our Br on 2 and our double bond broke. Okay, which means now we actually know what compound Q is. And if we are looking at butane and how butane, a single bond, can go to another single bond, considering our double bond actually had to break based on our interpretation with this middle arrow over here, it means that a single bond to a single bond is just substitution, because here substitution is just 1-to-1, which means we can just write substitution over there. Cool. And that would earn us 1 mark over there. But for the sake of understanding, it means that we had a butane, something like this, with single bonds throughout. And then all we had to add was a bromine over here, a Br2 potentially, because bromine's a diatomic molecule. But with that, if we added a bromine over there, we would just swap out this H with a Br. And that is what's happening with a substitution like that, which means it was a straight chain with single bonds throughout. There were H's everywhere, and we just added a bromine to live here, and that would just swap out with the H, meaning that this is just halogenation if we want to know this specific reaction that is taking place. But either way, we earned 1 mark over there. And then 4.2.3, write down the type of reaction represented by M over here. Okay, so once again, with the same train of thought, we're trying to see we have the thing here, we do not have the thing thing here and we do not have the thing on the line, which means we don't have enough information to work with this yet, which means we have to go to the second closest thing, which is this way over here, the bottom left, where our alkene reacts with HCl to form a major product and then a minor product. Okay, so what we need to do is first work with this portion here, which means we have, back to our drawing, we have prop 1ene, and then we're going to add an HCl, which looks very similar to our HBr. It is an acid, but we do not have to be concerned with the fact that it is an acid. We're treating it as if it is a hydrohalogen, which means just like this guy, we broke the double bond in order to attach the H and the Cl, which means that our double bond breaks, and then we add an H over here and our Cl over there, and the HCl joins this guy, forming the major product. And then one thing to keep in mind is the difference between a major product and a minor product, because right now there was no little byproduct that broke off. It's not like we have a plus H2O somewhere or something like that. If we were doing the reverse reaction for this, if we were to look this way with our arrow going like this, we would then remove our H, our Cl, that line, this line, form our double bond over there, and then our byproduct would be HCl, and this would be the minor product in most cases. That is what we refer to, especially in an elimination reaction. But in this case, they aren't referring to that. What they are referring to, though, in this specific example, is that now we have compound R, which fortunately for us, we're going to draw in 4.3, or we already have drawn it. So that's good. So we have the major product, but we do not have any HCl or H2O branching off as the minor product. But what they mean in this case for a minor product is the different probabilities of where the H and where the Cl will attach on our butane chain. Okay, because our H attaches here and our Cl attaches here, it's very common when a double bond breaks for our chlorine, our iodine, our oxygen, whatnot, to attach on the second C. It is because this is more stable. But with probabilities, sometimes the opposite can occur, meaning our Cl can join there and our H can join here, which means our Cl joins on the 1 over here, which means we have something like chlorobutane instead of 2-chlorobutane as it previously was. And a situation like this is called a minor product because it is far less common, because it is far more unstable when something like this occurs, meaning it is much more likely to break off and then form back into its usual product. Okay, so that means this is our minor product, and we've done all of that thinking just to see what our minor product is, to then go from this product back to our butene. Okay, which means we have to see that we have a single bond like this with a chlorine on 1, and that is the reason that our double bond is going to form on 1 over there again. And then what we're going to do is we're going to remove the chlorine, remove the H, and with that we're going to remove that line and this line, and then a double bond has to take place. And what this means is that we had a single thing, and then it is breaking off, forming a double bond, and then our byproduct is our HCl in this case, meaning the HCl that we removed there and there is now floating off in that beaker. Okay, which means we now have a double bond and a product, which means we went from 1 to 2, which means we're dealing with an elimination reaction. Okay, and the specific elimination reaction is dehydrohalogenation. We removed our H and our Cl. If it was hydrohalogenation, means we'd be adding it. But dehydrohalogenation, dehydrate, dehydrohalogenation means we are removing it, a hydrohalogen, from the compound. Okay, which means we can write dehydrohalogenation or we can just write elimination, and both will give us the marks. And in this case, just having written elimination earned us 1 mark over there. Okay, cool. And then 4.3 over here says write down the structural formula of compound R. So compound R, as we were talking about, is the major product that we were referring to in our previous explanation. Okay, so once again, we'll just do it quickly. We were dealing with our alkene over here, but then as we were talking about, the fact that we are adding an HCl means this double bond has to break, and we now have to add the H over here and the Cl over here on the second. Okay, and we don't add the Cl on the 1 because that is far less common. That is our minor product and less stable, which means if they aren't referring to major or minor products and there's a double bond over here on the first, always attach whatever joins our main chain, always attach that to the second carbon. Okay, that is just a good habit, and they don't always explain that, but that is what this means as far as stability, and that is why it is more likely to join our second than our first. Okay, cool. And then in the test, just draw all your other H's, and then we will get our marks. And we just earned 2 marks over there. And then 4.4 says for reaction N over here, write down 4.4.1, the type of addition reaction. Okay, so they want the specific type of addition reaction, meaning we cannot just use one of these guys. It is an addition, we just have to know what type of addition reaction it is. Okay, so we have an alkene, we have something plus something else goes to our alcohol over there. Okay, which means if we're back to our initial, like this guy, then in order for the alcohol to form, and we know it is addition, so it is 2 to 1 still, it means our double bond is going to break, and we're going to add something here and then something here, and our something here is going to be an H, and our thing over here, because of stability, always added onto our second C, will be the functional group of an alcohol, meaning it'll be our OH, our hydroxyl that makes it an alcohol. Okay, so right now we added an H, an O, and an H, meaning that these guys all joined here, which means that these weren't there before, which means that on our line over here that they didn't write, we have plus H2O, because that is what we're dealing with here. I'm missing H2 and the O over there, and that will give us a full happy alcohol as our major product over here. And once again, they refer to major product, not minor product, meaning our OH is on the 2 over here. Okay, which means the type of addition reaction, we're dealing with hydration because we added water. Okay, and that just earned us 1 mark over there. So then 4.4.2 says 2 reaction conditions. Okay, so if something is hydration, it means that we need water present. Some other reactions require no water at all because the water will then interact with it. But for this thing specifically, hydration needs the water, so we need water, and that is 1 mark. Or writing excess water. Both variations will work for this answer. Okay, so we do need water, we need excess water for this hydration reaction to take place. And then the second requirement is some sort of catalyst. And when in doubt, we write sulfuric acid. We will learn the different forms, but if we don't have time to cover everything before a test, sulfuric acid or H2SO4 is a very common catalyst in a lot of reactions. Okay, which means we need a catalyst, we need enough energy for this to take place, and then this catalyst specifically is our sulfuric acid, our H2SO4. But when we look at our reaction sheet that our teachers have given us, sulfuric acid comes up quite a lot, and in a lot of the past papers I've seen H2SO4 as a good shotgun approach when we're talking about the catalyst that we're working with. Okay, but we'll learn each specific one as we work through different examples, but this is the catalyst that we're working with here, and when in doubt I would recommend just putting this down. Okay, and with that we just earned 2 marks over there for the 2 reaction conditions. And then 4.4.3 over here says the IUPAC name of the alcohol that forms, which means we have already drawn it here. We know that our OH is on the second C in our carbon chain, and they told us it is a major product, and that is also why it's on the second C and not the first C. Okay, which means our IUPAC name is meth-eth-probut. So we have butane, and then our functional group, our OH, our hydroxyl, is on 2 over here. So we have 1, 2, 3, 4, 1, 2, 3, 4. We always start our counting from the closest C to where our functional group is attached. Okay, which means we have 1 over here, 2 over here, 3 over here, and 4 over there, which means we're dealing with a 2. So we have butane, 2, and then ol. Butane because there are 4 C's in the chain, 2 because that is where our functional group is attached onto the second C, and then ol is the prefix that we have for an alcohol ending in ol like that. Okay, and then 4.5 over here says write down the IUPAC name of an isomer of butane. So it's 2 marks, and our butane is up here. Okay, so we have 3 different types of isomers. We have functional, we have positional, and then we have structural. Okay, the thing with butane specifically, if we have our butane over here, is that there is no functional isomer for butane because there are single bonds all around and we don't swap something. It's not like a ketone and an aldehyde or a carboxylic acid and an ester when we can just remove something or add something and change the functional group but keep the same amount of C's and H's. With any alkanes, we cannot do that. So our functional is ruled out. Okay. Positional is also ruled out because there's no double bond that we're moving. It's not like there's a double bond on 1 that we can then go ahead and move to 2, for example. So it means that positional is out because there are single bonds throughout, so there's no variation that we can do with the attachment for the functional group. Okay, which means our last arrangement is structural, which means for a structural isomer, we have to break the main chain and add a side chain over there, which means this is gone and we no longer have butane, but now we have our C branching off on the second C over here. A reason we can't add it on 1 or 3 is because it would still just be a long butane, just with a bent chain instead of a straight chain. Okay, which means we have to add our C over here in the middle, and then we're dealing with something different, because now our main chain is only 3 C's long, and we have a methyl attached on our 2. Okay, which means we are dealing with a structural isomer for butane, and when we do the IUPAC name, we always have to start with our side chain. Okay, so if we count either way, we're going to be on 2 over here, whether we counted 1, 2, 3 or 1, 2, 3. Okay, which means we're dealing with a 2 methyl, so we can have a little dash or hyphen in between there. So we have a 2 methyl, and then we have our long chain, meth, eth, propane. Okay, and there aren't any specific bonds to deal with, so we don't have a prop 1-ane or a prop 2-ane, because that only works for enes and ynes. So right now we just have our branched side chain where our methyl is attached on 2, so we have 2 methyl, and then we have our long chain, which is our propane. Okay, cool. And with that, we just earned another 2 marks. We can have a dash in between here, or we can remove the dash and put those two together like that. Both work, but either way, we wrote down the IUPAC name of an isomer, the structural isomer of butane, which is our 2-methyl propane, and that earned us 2 marks. Cool. And then last question, 4.6. And 4.6 over here says use structural formula to write down a balanced equation for reaction Al. Okay, and structural is in capital letters, so that's important. And this is for 5 marks. So structural formula for a balanced equation for the reaction of Al, where we have our alcohol joining up and forming our compound Q, which we saw was our haloalkane. Okay, so structural formula to write down the balanced equation. So let's write down the alcohol first, because we had drawn that previously, which I'll rearrange for us here, and then compound Q, and then we can see what we need in order to form it. Okay, a reminder for our alcohol, we had butane 2-ol, which means our O and our H was over here. We had an H over there, and H is throughout. Okay, which means this was on our left side of our reaction. This is one of our reactants, and we need to see, is there another reactant on the left or another product on the right, or what? But we'll get there. But we do know what compound Q looks like, because compound Q was our HBr when we broke our alkene and we added an H and a Br over there, which means it looks very similar. We just have something like this. Okay, and that means what we have here is a substitution, because this was here before and now this is here afterwards, which means our OH was swapped with the Br and the Br joined it after the arrow. Okay, which means we aren't dealing with an addition reaction or an elimination reaction, because there isn't 2 to 1 or 1 to 2. There are no double bonds breaking. But that means, as we mentioned, we're dealing with a substitution where we go from 1 to 1 or 2 to 2, which means we can't just go from 1 to 1 over here, because we don't have the other parts to replace them. We're missing some of the parts for all of this math to add up, which means we have to go from 2 to 2, which means what are we missing on this side? And the most common way is to not just add a Br and an OH, but to add an HBr. This is something that is on our reaction sheet, and this is the most common one when turning an alcohol into a haloalkane. Okay, so we add a HBr over here because the Br is missing, and we need this Br to join over here and this OH to join that H over there, which means once this Br has joined, what we have on this side as well, because a reminder that we're going from 2 to 2, is our H2O, because this OH joins that H when this Br joins over there. So the Br swaps with the OH and this OH joins this H over here, which means we have H2O, and that is what we have on the right side over here as our product, which means we have just completed this question and we don't have to write HBr like this. We can, considering they ask for structural formula, but HBr like that is also okay. And we also don't have to write HOH, something like this for H2O, because H2O is also okay like that. When they're referring to structural formula, they want us to just draw the structural formula of our organic compounds. Okay, and the structural formula specifically, not the condensed structural formula like CH3COH. We will lose marks if we draw them like that. Okay, so right now we have written everything. We've written the structural formula correctly where they wanted the structural formula, and we were referring to a reaction Al, and then we just need to see, is it balanced? And if something is going through substitution, we can by all means count all of the H's, all of the O's, all of the C's, all of the BR's. But if something is substitution, it is swapping identically. And that is why we add the HBr here instead of just a BR, because that would make it a bit trickier to add the BR and only swap one thing, because then we'd have an OH over here, and that is less likely to occur as a product by itself, because OH is something from acids and bases, and that is a hydroxide. Okay, which means adding an HBr and swapping it with the OH means that everything is balanced and that we don't have to add any numbers anywhere. And usually when they're referring to a balanced equation in structural formula as well, we don't usually have to add numbers. So it just means we have to add the right reactants with it in order for it to remain balanced throughout. Okay, cool. And that just earned us 5 marks over there and 20 marks for the whole section. Great job, guys. Let me know if there are any questions in the comments below, and otherwise I will see you in the next video.